Recording. Marcia, please.
Okay, so again, let's move to our second talk of this afternoon. We thank you all for being here, your interest and time spent with us. We are honored to welcome Professor Fabio Ramos, who will speak on controlled latent diffusion models for 3D porous media reconstruction. He's an associate professor in the Department of Applied Mathematics in Universidade Federal do Rio de Janeiro, and he holds a PhD in math from UFRJ with research periods at University of Chicago, Indiana University, Weizmann Institute, and Hausdorff Center for Mathematics. His work lies on the intersection of applied mathematics, fluid dynamics, and modern machine learning. We're very glad to have you here. Let's get started.
Thank you, Marcia. Thank you, Juan, for the kind invitation. So guys, so you see there are a lot of controlled, latent, diffusion, porous media, a lot of parts here. So it's difficult to wrap it up at the end of the talk. So if you have any questions, please just interrupt me. It's better this way. You can really interrupt me anytime, right? So let's start trying to understand what learning is in this context, right? So I'll start trying to explain the latent word here, right? So learning, this is a picture of an autoencoder. This is a neural network that gets an image and it downsamples the image. So you have a large representation of the image, like the full representation. And then you downsample and you make a very small representation of it through this bottleneck. And there's another part of the neural network that recovers the image. So somehow there's this mantra in learning that you have to go through bottlenecks. You have to compress information, right? So what this neural network does is you get the data, you make a very small dimensional representation of it, and then recover it. This space here, it's what I call the latent space. It's really a small time space. So what do you mean by learning? So a good student, to say that he learned something, she learned something, the student should be able to summarize, right? Should be able to say the story in few words, right? And then by himself or herself, they can regenerate the class, right? So you're able to summarize and regenerate. So it's learning is encoding, like compress information and able to regenerate. So why is it important? Because if I just give you a hint of the picture, a very low resolution of the picture, this network is able to reconstruct everything just with a little hint. So again, this idea of compressing, encoding, and then generating. This is the idea through an autoencoder. And so we believe this works because we believe that data, like meaningful data, they live in a very small dimensional manifold. So they're embedded in a high dimensional Rn, but it's the topological geometry is actually pretty small. So this is the idea of the manifold hypothesis. So there are many ways of encoding, right? This is Jimmy, my Chihuahua, and you see I can encode Jimmy's picture by adding noise, right? So I can add a lot of noise, and the meaningful data is just very small. Like I can just see a glimpse of his picture. But I've seen Jimmy so many times, so many pictures, that just from this very noisy data, I'm able to reconstruct his picture in my head. I learned all the possible representation of Jimmy because I have this very large data set of his pictures in my head, right? And this is why this method works, right? What I'm saying, what we'll see, is that given a probability distribution, we are able, through a noisy process, to compress information of this probability distribution into a very small, non-informative probability distribution if I know the process. And if I know the process, I can go from pure noise to recover the full probability distribution, right? And this is the idea of diffusion probabilistic models, right? So before any of you fall in love with any of these people here, I gotta tell you they are all fake. These people do not exist. They've been obtained through this diffusion model. We trained, so the Ho and his co-authors trained in this 30,000 high quality celebrity faces. And what they do is the following. They get like one of those pictures, they add a lot of noise, they encode, and they know how to, they know how to regenerate from the encoded data. So they do this with Tiger Woods, with Angelina Jolie, with Brad Pitt, with I don't know who. And then at the end of the day, because he can decode the very noise observation, now the person can sample a completely random noise and say, okay, try to generate a celebrity. It will not generate an original face, but will generate something similar. So these people will all be very beautiful, attractive, etc. So this is what's behind this DALL-E software that you see on OpenAI, right? And ChatGPT, that's how they generate images. So here, what I'm trying to do is to generate domains for simulations and porous media. We're trying to have this regenerated. That's what I call reconstruction, right? So we get this large data set of rocks, and then we add noise and learn how to denoise, right? And once you learn how to denoise, we sample a random noise and they say, okay, try to generate a rock, and you generate a version of a rock. We are using here the framework by the EDM framework by NVIDIA, and that's mostly what I'm going to talk about here. So in this project, we'll have this, we are able to generate pore scale images of several families of rocks, sandstones, carbonates, anything. And the goal of this project, it's a collaboration with ExxonMobil in Houston. The idea is to build this reconstruction model that will be trained on micro CT databases and 2D optical and FIB-SEM images, 2D slices, and some descriptive characteristics. And from it, we're able to generate lots of pore scale domains for simulation, right? And then we can do all sorts of uncertain quantification of porosity, permeability, etc. So far, we are able to generate 3D CT binary images with resolution to 256 cube. So if you want to check it out, we have a version in archive. It's a collaboration with Danilo Naif and Bernardo Schaefer, which are PhD students in the group. Gustavo Pires is in the geology department, and Dragan Stochkovich and Thomas Rapstein in the ExxonMobil in Houston. So that's most of what we're going to talk about today. But, we are in an audience of mathematicians, so I'm not going to focus a lot on the porous media. I will mainly explain about diffusion models. So please, again, interrupt me at any time because there are a lot of little details here and there. All right, so the idea is that you have a probability distribution of rocks, right? Of rock images, and we want to approximate this probability distribution by some model distribution, right? Why I want to do this, because what I mean by approximating, I want to be able to generate a sample from this probability distribution. And I want to do conditionally sample. I want to say, I want to think of a very porous sandstone. Can you give me 4 examples? And I generate for you 4 domains with very large porosity. I also want to say that given an image, this is a very high probability image, or it's a very low probability image. So I would say, well, typically these images they fall within this range. So that's the kind of thing we want from an applied point of view. what's the problem? The problem is that to approximate the original distribution, you have to do some maximum likelihood, some optimization strategy. So you parameterize with some parameters theta, and then you have to, I don't know, maximize the likelihood of this probability. And then the problem is that you have to calculate this z theta, the normalization of the probability distribution. And this is an integral. This is an expectation in a very high dimension. So you have to be able for each theta to calculate a very complicated integral. And life is weird in very high dimension. It's very difficult to calculate integrals. There's all sorts of concentration of measured results. And that's what I try to avoid here. So what do? We try to sample by following the gradients, right? So let's sample by looking where's the mass of the probability distribution, right? This is the kind of thing we're trying to do when we sample. And then instead of looking at the gradient of the probability distribution, you look at the gradient of the log of the probability distribution, and there's a reason for this, right? Because when you calculate the gradient of the log of probability distribution, that's what I call the score function. You open up here the calculation, and the normalizing constant vanishes. So you don't have to worry about the normalized constant. But this is one important reason. These ideas you can find here. And then instead of approximating you approximate the score. So you try to follow the gradients, and then you have to approximate the score to be able to do this. And then you don't need to worry about normalization, right? The problem is that it's difficult to approximate the score function in very high dimension because this grad will be somehow ill-posed. It's difficult to numerically calculate in low density regions, right? But let's assume that you can approximate the score. If you can do this, then you can generate samples by doing something we call Langevin dynamics. So how it works, you initialize a chain by sampling from a very easy prior, like Gaussian. And then you follow the gradients. You follow the gradients of the log of the probability distribution. And then you go and then add some noise. And then you go step by step until it converges. And then you say, okay, this is a sample. And there are a lot of theorems saying that, well, under some hypotheses, it works. The problem is that in high dimensionals, usually you initialize in a very low density region, right? And second is that if you're in a very low density region, then you have inaccurate approximation of the score. So the Langevin dynamics will not work because you don't have a good approximation for this. So Langevin dynamics is an old idea, but it doesn't work in practice. So what Song and Ehrman, so these are two guys from Stanford. Song was a PhD student here. So they came with the Langevin annealed version. So what you do is like, okay, I want to sample from this guy. What I do a perturbation. I perturb data, and I have a very field probability distribution, right? There's no low density region here, right? The problem is that, and then I do Langevin here, but the problem is that this perturbation is very far from the original probability distribution. So how to solve it? And then you do an old idea, is the annealed Langevin dynamics. What you do, you create a family of noisy distribution, right? And so that for this distribution, it's easy to sample. And then you sample from here, you parameterize the score function for this noisy version. You parameterize with some neural network. And you do this for lots of noise levels, right? From the very low to the very high. And you train a neural network for all the noise levels at the same time. And then you do Langevin dynamics step by step. You do Langevin here, you stop, and then you lower the noise, and then you do Langevin dynamics, stop. And that's the picture, something like this. You go for very high noise, and then you start sampling, lower the noise, start sampling, lower the noise, start sampling, and then you can cross the low density regions. So this is the idea of Song and Ehrman in 2019. This is just a 1D version. So we are trying to add a lot of noise, and then I want to be able to denoise it. And that's the way of doing this sampling, right? So this is the annealed Langevin dynamics. This is 2019. But then Song and Ehrman and the guys from Google Brain, they came with this version that they add noise by solving a stochastic differential equation, right? And then after this, 2 years later, Karas and his collaborators in NVIDIA, they expanded this version. That's the EDM framework I'm going to talk about. So this idea of adding noise and reversing noise, there's a very natural framework to do this, is through diffusive stochastic differential equation, right? So you just get this initial data and evolve with some drift and some noise, right? Until you reach a Gaussian distribution-like distribution. And then there is a nice result that given a stochastic process, there is a reverse stochastic process that is given by this formula. And, surprisingly enough, the score function is here again. So you can add noise and remove noise through the framework of stochastic differential equations, right? I cannot do a full review of stochastic differential equations, but when I write something like this for the students here, what I'm actually saying is that this, in the integral sense, this is the normal integral, the deterministic one, and this is what I call the Ito integral. And you can think of some limit, just like a Riemann limit. But at each time step, you have a Gaussian distribution, right, with variance delta t, and you're weighting the normal with this noise, and it's calculated in the beginning of the time interval. That's what I call the Ito integral, right? So that's just, in a nutshell, what the stochastic differential equation is. At the end of the day, these are stochastic process. So the Ito integral is a stochastic process itself, right? So for example, these are trajectories of this Ito integral, right? So I'm integrate with Euler-Maruyama method, this function square root of 2t, right? So you have trajectories. All right, so let's get back to the noising process. So how do I add noise? Well, you can give your initial data, my Chihuahua, and for a given level of noise, I just add sigma times normal distribution. And then the marginal distribution of this stochastic process is just the convolution of the original P0 with the Gaussian distribution, right? And then let's do some PDEs. If you differentiate with respect to sigma, so somehow I'm evolving with sigma, is that if sigma was my time, right? I'm parameterize time with sigma. If I do dp d sigma, I get this expression. And if I differentiate 2 times with respect to the space, you get this. So you have some sort of Laplacian equation, right? So dp d sigma equals sigma Laplacian p sigma, right? So it's just an easy fact. So the marginal distribution satisfies this PD. There's a whole family of results that we call the Fokker-Planck equation. So there are like a lot of versions. So for this version of the stochastic process, fxtt, and here my noise is just a function of t, not of x. For this framework, my Fokker-Planck equation can be written like this. So the marginal distribution of this stochastic process satisfies this PD, right? And now if you look at the last slide result, our PDE, and take a look here at the Fokker-Planck equation, we actually see that this equation is the Fokker-Planck equation of this stochastic process. So what we see here is that thing of adding noise with Gaussian is actually solving this stochastic process through these lenses, right? So this addition of noise, that's what I call my forward stochastic differential equation. Now, when you look at this equation, right, my PDE, I can write this in this funny way. The Laplacian is the divergence of the grad, and then I use this log trick. The grad of P is the grad of log P times P, right? And I use, again, the Fokker-Planck equation. And then I just check what I'm doing here. So the divergence here, so the divergence here. And then I just compare. And then we see that actually the marginal distribution, because it solves this equation, it's also related to the solution of this ODE. So it's the Fokker-Planck just looking at the deterministic time. So my marginal distribution of everyday noise can be seen through two angles. I'm moving forward with this diffusion SDE, or I am moving forward with an ODE following this vector field, which is our score function. So that's how the score function shows up. So I can add noise by solving this SDE or moving my initial probability distribution with an ODE. And then the fun thing is that because it's an ODE, well-posed, etc., I can play it in reverse. So that's how I can go from pure noise to the original data, because I can just do a reverse ODE, right? And then a key observation in diffusion models that I can approximate this sort of thing with neural networks. That's what I'm going to try to convince you. One more thing, SDEs can also be reversed. So given this SDE, this diffusive SDE, I have a reverse SDE given by this equation, right? So it's more general, right? This is a result by Anderson, 1982, in this stochastic process. And the Fokker-Planck, so given an SDE, right, the SDE reverse time can be written like this, where this W bar is the standard Wiener process, but you have to do this trick. And then you have a Fokker-Planck in reverse time. And then what you can do is to split this Laplacian in two ways. I add an extra parameter gamma, and I split it in two parcels. And then one component of the summation, I will relate to the ODE part, and the other one, I will relate to the SDE part. So here I will do the log trick, and here I will not do the log trick. And gamma, I can play with it. So that at the end of the day, I can propose a reverse Fokker-Planck that is a little bit deterministic and a little bit diffusive. So I can play of how much noise I can use to reverse the SDE. And this is the Kara's framework. Summing up, given a stochastic SDE, I have a reverse time SDE given by this expression, where I can mix a little bit of deterministic probability flow D and a bit of diffusion. In the limit, when gamma equals 0, it's ODE, and when gamma equals 1 is SDs, right? Just you can generalize this. You can add noise and scale this original signal, right? And this gives rise to a lot of families. So there are a lot of diffusion models here. I'm not going to talk about this. Our framework, the EDM framework we're using, alpha equals 1, and I'm adding noise linearly in time. That's what I'm trying to do. And I add so much noise that at the end of the day, I will have something that looks like random Gaussian noise. And then I can integrate back through ODEs or SDEs. And I use usually this numerical integration that I call the Helm method, which has this amount. So summing up, let's say we train. So what do? We add diffusion to the whole data set I have. right? So I go from here to there, adding a lot of diffusion and so much noise, that at the end of the day, I have a Gaussian distribution. And what I do to generate, I sample from the Gaussian distribution because it's easy to sample Gaussian distribution. And I integrate backward with SDEs or ODEs, and then accept my final image. What's the challenge? The challenge is that to solve this ODE or SDE, you need the score function, the grad of the log of the marginal probability distribution. And so, okay, I have to minimize this loss function, right? I have to approximate the grad of the log of P, right? And I'll do the expectation with respect of all noise and all trajectories. So the role of the forward trajectories is to train the score. To solve the problem backwards, I don't need the forward. I just need the forward to train this score function. But it's difficult to calculate the score of the marginal probability of this diffusion model. But what is easy is to calculate the score of the marginal distribution if you know the original data. So the score given x0, if I know that it's a diffusion of my Chihuahua, then I can calculate the score, because then it's just the normal distribution and the grad of the log is just this, because it's from the normal distribution, right? So here we have an opportunity. If I change the objective from approximating this to approximating that, it would be easy for me. But why can we do it? That's a beautiful result by Vincent and before Hivarinen, is that, yeah, you can do this because of this theorem. If I have a regional distribution and I perturb the distribution with some kernel, right? Then if I define the loss function, it's approximating the noisy score, and this loss is approximate the condition noise, and then I take the expectation with respect to all initial data. Then this loss equals that loss plus some constant. That's what I call the score matching trick. So what I'm saying is, instead of approximating this score, you approximate the condition score, and then you take the expectation with respect to all the initial conditions. And then minimizing this loss is equivalent to minimizing that loss, and that one is easy. So this is the score matching trick, right? So we will approximate this guy here, the condition score. So I want to approximate this guy. I want the minimum of this. So a natural parameterization is to write S as a D minus X sigma over sigma squared. Why? Because when I write like this, I add this thing here, and I look at this expression, this X sigma will cut with this X sigma, and at the end of the day, what you have something like this. You have to minimize this loss function, which is the D of X sigma minus X0. So what I'm talking about here, I start with my Chihuahua, my X0, and I add a lot of noise to the level sigma. And what this function is trying to do is to get back to the original Chihuahua. And I'll do this for another dog, and then another dog, and another dog. So if I do this for lots of dogs and lots of noises, then I will learn the score, because then I plug it here back, and then I just know the score. So this is the idea. All right. So how do you train then my score function? I train my score function like this. I start with my original data, like this truck, this airplane, other modes of transportation, and I add noise. And I add noise to the other guy, right? And then I just pick a noise level. So I pick this noise level, this airplane with a lot of noise. So what the denoiser is trying to do is to get back to the original airplane. And what it does is you give this. So you don't get the original guy. You get a denoised version, which is pretty similar to the original guy. And then you pick another noise level, this very high level. And then you try to compare to the original truck. But what you get is this image that's not even a truck, but it's something. It looks like a car, right? Because it tries to resemble our original data. So it's a car, and then, okay, you miss it, and then you try again for the truck again, for another level, and then you get this instead of that, and you do this for a lot of data, a lot of noise, and then you try to minimize this error, and you minimize this by training a neural network that approximates this denoiser function, right? So once you learn this function with a neural network, you plug here, and voila, you have your score function. And the key observation is that we can approximate this with lots of neural network tricks. Usually people use a simple U-net. A U-net also has this thing of compressing and generating with some skip connections, but we can learn this, right? So once you learn the score, so what you have to do now is to solve the reverse SDE. And then, so how we do? We sample from the Gaussian noise, and you calculate the score with my neural network, and I plug it in the ODE, and I go one step back. And then I calculate the score with my neural network, I plug in the ODE and go one step back, and do this again until I get the original image. And then you have lots of choice, and it's pretty expensive and difficult to train this thing. You need big machines. We have some big machines in the project. So I'll just finish with in this last part of the talk, I'll talk about how we use this to then generate rocks, right? So first of all, here this is a histogram of the porosity. The original porosity histogram is like this, and our generated porosity is like that. So you see that we cannot fully recover the porosity distribution. We have what we call a mode collapse, right? We're not able to generate everything. So somehow we are not in the correct space. The pixel space is too large to learn, right? Remember, I have to avoid low density region, and a very large ambient space is more difficult. So what I do, I train an autoencoder, and I pass this image through to a latent space, and I train the diffusion model in the latent space, right? Usually the latent space has more channels, but in average, so I divide by 8, 8, 8, but I have 4 channels. At the end of the day, I have 128 compression. There are many ways of training a variational an autoencoder. We use what I call a variational autoencoder. So we're able to map a point to a normal distribution. I don't have time to talk about this, but our loss function is like, I want to minimize the decoding error. I want to encode and decode and recover everything. So I minimize this guy, but I'm penalizing my latent representation. I want my latent representation to be close to some normal distribution. I don't have time to talk about this. So use this sort of variational autoencoder. And what we do, we map the data in the latent space, and we train a diffusion model in the latent space, right? And once you train the diffusion model in the latent space, I sample a noise, sample from the Gaussian noise, Gaussian distribution in the latent space. And then I run my reverse flow OD in the latent space. But here what I have is a latent representation. And then I have to pass it through the decoder and then recover the full the full image. So this is what called the latent diffusion model. I don't have time to talk about this, but I just want to say that our autoencoder is very good. We train in the 4 rocks at the same time, but there's a nice properties that we have these 4 rocks, and then we train an autoencoder in a different rock from another data set. And you still can compress data here. So there's a universality of rocks, right? So we tame the mode collapse. It goes from this to that, right? For 128 cube, these images are so large that we cannot do diffusion model in the pixel space. We have to do in the latent space because of memory and computational struggle, right? So here is the porosity, the permeability. This is the main statistic we want to recover. So we recover very well in 128. And for 256 cube, we have to go to the latent space because it's too large image. And moreover, we don't have many images. We have to do data augmentation. So if you look here, the porosity, we are generating crazy rocks. When you do data augmentation, we generate good rocks, but with mode collapse. So we see that we're generating bad rocks. So what we do, we control the latent diffusion generation. So that's another aspect of diffusion. It's very easy to generate with control. I can say, well, condition on the porosity value, generate lots of guys with 0.3, 0.4, 0.2. So I can generate with control. I don't have time to talk about this, but essentially your data now has labels, the porosity, the race, the type of dog. So you have the labels, you have the joint probability distribution. And I want to approximate the condition distribution, right? That's my goal, so that I can easily sample from this. And I do the same. It's just the same. My loss function now, the expectation is in the joint distribution, right? And the learning is the same. I train a denoiser, but you have an extra input, which is the label, the porosity value, for example. And I take the expectation in the joint probability space. So it's essentially the same thing. It's easy. So we generate easily with control porosity. So this is like the porosity histogram. You see I'm condition 0.05, 0.15, and I can generate easily. It's nice to see that if you try to invent rock, generate very low porosity rocks, when you don't have available data for this, you get pulled back to the mode. So you cannot dream about rocks that don't exist, right? You can condition on function, on 2-point correlation. This is a new thing we introduced. We condition with a transformer network. And yeah, so again, we can sample from the porosity value, and then given this porosity value, I sample a new rock, and I do this Gibbs strategy, and I recover just by controlling on porosity. I recover all the statistics. So that's why it's controlled. I can just look at one characteristic and I control all the other characteristics. So this is our work. We did more validation by working with permeability. We don't have time to discuss this. So in conclusion, in this work, if you want to generate an image of rocks, you should go to the latent space. It just works very well. We are trying to upscale this for larger images. And I just want to give a final remark. These diffusion models are so flexible that people have been using it in autoregressive ways. So there's this beautiful work by the guys from Google. It's in Nature 2025. They do an autoregressive diffusion model for weather forecasts, and this is one of the best weather forecast models available. And we are working with ExxonMobil as well in this front to have a forecast of ocean models. We already have results for simple geostrophic models, and we also have some results for full Navier-Stokes. And so it seems it works, right? Okay, guys, sorry it was a little bit too fast, but that's it. Thank you.
Thank you, Professor Fabio. Do you have any questions or comments? I have a general question, then I have little ones. First of all, I loved your talk, and I think we should exchange some ideas. Well,
Okay, I'm here. I'm available.
yeah. The first thing is a general one. What is the difficulty in integrating modern machine learning techniques with kind of classic or traditional fluid dynamics theory and this kind of stuff?
Yeah, that's so much. This is so in 2025 we had two talks that were very good. I really so there's this talk in the joint mathematical meeting, the JMM, this year. So the Gibbs lecture this year was given by Yann LeCun from the Meta, right? And he was talking about the difficulties of machine learning for physical sciences. Why is it so difficult? And there was another talk, it's the GTC meeting by NVIDIA, it's like big conference as well. And the main talk was how difficult to do machine learning in the physical side. So there is this thing that, so the main difficulties I would say is that all I've showed here, dogs and rocks, so there are a lot of things, but so when you see an RBG image, right? The channels are very correlated. So if you get right one thing, you get right everything else, right? They're very, very correlated, right? And physical problems and fluid mechanics, you have lots of relevant channels. Right? You have pressure, you have vorticity, you have UV, W, you have enthalpy, you have whatever, you have so many things. And when you look from the point of view of machine learning, they are not at all very correlated. Things can happen and they have like multiple time scales. Some stuff regularize very fast, other take. So for example, Darcy flow, right? Like pressure buildup is very fast. And then the flow itself is lower. And then, so things have multiple time scales and they are very uncorrelated. And when they're correlated, it's not trivial. So somehow vision is easier because things are very well structured. Like physical sciences, you have lots of uncorrelated channels and dynamical channels. And this is difficult and we are struggling. We are struggling. We're really struggling. I think that's the main problem.
When you said in the beginning that you had some issues with integration, what will those issues be?
Integration. Okay. The thing is, so if you want to integrate a very high dimensional probability distribution, you have to be able to do a Monte Carlo simulation. You have to be able to sample from it. And usually what you do is something we call accept rejection sampling, right? You try to control with something that so what you actually know how to sample from is Gaussian distribution. That's what you know, right? And then you have to be able to control the probability distribution that you want with Gaussian distribution. And in very high dimensional space, for several reasons from information theory, it's difficult to control with one single Gaussian. And then you have all this Markov chain Monte Carlo method. And then you try to control locally, but then how local you have to control is too local in very high dimension. And then, so somehow you have to, it's like the random walk, like the drunk's walk in high dimension, the drunk will never get home because he has so many directions to go that he will miss his street. So in low dimensional, you like the random walk drunk guy, he will eventually get home. But in very high dimensions, and the other thing is like the concentration of measure. The most of the mass of the ball in high dimension is very near the sphere, the thin shell. And then this makes, so you have this property that data points are somehow equidistant. So everybody is far from everybody in very high dimension. This is a weird thing. So if you're the drunk guy and you're very close to home, and you just give a misstep, you cross the whole street, the whole city. You go very far away. So in very high dimension, if you miss a little bit, you miss a lot somehow, because you can miss completely in one direction. So high dimensional integration, you just cannot do it. So you have to avoid it. That's essentially the thing.
Let me see if I got it right. You were saying that this not having noise, it's not, one should expect not having noise in order to get things right, I would say, but this is not okay, like the best approximation. So this is why you put some noise and then you somehow keep it there and you control it, I would say. So, but when you get what you called the reverse probability flow ODE, wouldn't you expect to have an SDE and it would fit better the approximation or the reverse situation?
Or the last part I didn't get. So when I have the reverse,
instead of having an ODE or of transforming it to an ODE, to have to try to keep in your head the SDE theory, so that you won't lose something, I would say.
So you reach a point that is like very crucial. So this work by Caras, this, by the way, that's an amazing work. It's really good. It's really well written. The appendix is amazing. And these guys are not even academics. They are in NVIDIA. So it's weird for me. But it's amazing work. So the whole point of this work is what you said. Don't throw it away. Keep the SDE and play with this thing. I showed you. This thing. So like, okay, you have this gamma, and gamma equals 0 have the OD. Gamma equals 1 have the full SDE. You should play with this and have a little bit of the two words. This is the thing of the flow D, there's an advantage. The advantage of flow D is that, for example, you can noise and denoise the same trajectory. So this is good, for example, for outlier removal, stuff like that. So there's some implications, like the reversibility from the deterministic point of view has some advantage. But for noise, for quality generation, keeping the full SDE might be important. And actually, in this project, we have our peer mathematicians team led by Ricardo Rosa and Glauco Valli, and they have this amazing PhD student, Bernardo Schaefer. They have some results they will publish soon that, you should keep the stochastic part, because you can avoid some trouble here and there. But surprisingly enough, for our application, the ODE was better. For the rocks, ODE is better. So we don't understand very well why, but I guess it's case by case. But so people, they don't throw it away. They keep
because you have big particles. In case you have small particles, you would have to keep the situation of small particles, and then not to come back, not to lose the diffusion of those small particles. Maybe this is my impression.
Yeah, it could be. It's this problem. The things that we also go to the latent space, and there you have to think like, okay, I'm not doing the regional space. There's a latent component, and then everything gets messed up. But I don't know.
Also,
but people don't throw away. But people don't throw away.
When you were talking about, you were kind of considering in the integral, your integrand was some probability, some conditional probability, and then it resembled me of averaging methods that you approximate things by autonomous things, but somehow it it came to my attention because then you have your conditional probability inside the integral, and you take another probability that does not. Yes, like that. Yes, and this comes for me with the idea of and it's not an average because you don't have 1 over something, but maybe it is implied there.
And it is a conditional expectation. And Gibbs sampling somehow is like this, right? Gibbs sampling is like, okay, let's do a Monte Carlo method, but sometimes it's easier to sample from a conditional distribution than from unconditional. So what you do is like you first sample the condition and then sample from the unconditional. So this is what people call Gibbs sampling in Monte Carlo literature, right? And but here we have infinite amounts of conditions because it's a rock. And then I say, well, you have S2, you have porosity, you have pore size distribution. I mean, you can come up with a physical feature, right? Any physical feature. And then I can say, well, I will sample from this physical feature and then I'll sample the rock conditional on this physical feature. We could choose any Y that you can calculate, right? We chose porosity, and then we are doing this conditional sampling with something that it's easy to calculate. This is the sort of idea we're practicing, and that's what controlled the. So somehow this works. This controls the. So in latent, somehow the idea is like if you want to use the latent space to sample, you have to bring from the real data, from the real world, some information. Because the latent space is really good to compress everything, but then maybe you lost some stuff there. And then you have, okay, this is my compressed rock, but this is the porosity. And then, okay, and now you can sample from this. So you're trying to bring back some information to the latent space and then conditionally sample. That's what we thought at the time. And it works.
And at last, I would like to just to make some comments. And you mentioned the E2 integral, and my love is integrals, and I'm coming to stochastic differential equations lately. So one integral that is equivalent to E2 is the so-called E2-Hanstorff, which gives a Riemann approximation for that. And also concerning these infinite dimensional spaces that you would, I would say path integration would maybe do the job for you. So possibly truncating in the dimensions, in the finite dimensions, say you have R to some say the interval AB, all functions from AB to R, but then you have an exquisite set R times R times R times R times R, but then if you truncate in the dimension and do some usual partition of each R, so perhaps I should visit my friend Rosa and you and spend some time talking with you. And when we can exchange ideas, because I'm coming into this now, and your talk was amazing for me. I've learned a lot.
No, these guys, Basia, it's unbelievable. These guys, they understand the problem from every single angle possible. So yeah, sure, you should come and visit us. Let's make it happen.
Okay,
all right,
guys, I would like to thank Professor Fabio again, and I would like to thank the presence of everyone, and I would like to invite you to our next session. We would be on April